Hello friends, I welcome you in lecture number 8 on vector calculus. In this lecture, we will discuss this question on finding scalar potential function for a given vector field. This question was asked in GTU summer 2020 exam for 7 marks. Here the question is, show that the vector field f bar given by 2xyzi plus x square z plus 2yj plus x square yk is irrotational, and find a scalar function phi such that f bar equal to gradient of that scalar function phi. So we know that f bar is irrotational if curl of f bar is a zero vector, and here we are asked to prove that f bar is irrotational. So we must find out curl of f bar, and we have to prove that curl of f bar is zero vector. So first we write down given function, and then we will try to find out its curl. Given that vector field f bar is x component is 2 times x y z I plus x square z plus 2y times j plus x square into y times k. And by the definition of curl, we know that curl of f bar is the vector product of del operator with vector f bar, and this vector product is given by determinant of, first we write down the sign of determinant. So this curl of f bar is given by, first row is unit vectors ijk, second row is partial derivatives with respect to x, y, z, that is components of this del operator, and third row is components of vector f bar. X component is 2xyz, y component is x square z plus 2y, and z component is x square times y. And now we try to expand this. This is equal to I times determinant of this matrix, partial derivative of x square y with respect to y, so x square is constant, derivative of y is 1, minus partial derivative of this quantity with respect to z, so we consider x and z as constants, so derivative of 2y square is 0 with respect to z, and x square is constant, derivative of z is 1, so this is x square minus x square times I, then minus of something into j. So for that we consider this matrix of order 2. So partial derivative of x square y with respect to x, y constant, derivative of x square is 2x, so it is 2xy, minus partial derivative of 2xyz with respect to z, so here 2xy is constant, derivative of z is 1, and finally we will write down determinant of 2 by 2 matrix multiplied with vector k. So for that we will consider this matrix of order 2, and we will multiply determinant of this matrix by vector k. So first we take partial derivative of x square z plus 2y with respect to x, so z and y are constants, 2y square has derivative 0 with respect to x, and derivative of x square z with respect to x is 2xz, z is constant, derivative of x square is 2x, and derivative of this with respect to y, so 2xz is constant, derivative of y is 1, so we have 2xz minus 2xz, and now we can see we have x square minus x square, that is 0, then 2xy minus 2xy, that is minus 0j, or because of 0 we can write plus 0j also, and 2xz minus 2xz, that is 0k, so we obtain 0 vector. So therefore we have shown that curl of f bar equal to 0 vector, therefore f bar is irrotational. This is the first sub part of the question. In the first part, we are asked to show that given vector field f bar is irrotational, and that we have shown by proving that curl of f bar is a zero vector, therefore f bar is irrotational vector field. Second part is to find a scalar function phi such that f bar equal to gradient of phi. So to find out that scalar potential, we note that here components of f bar are defined for all points in R3. These components 2xyz, x square z plus 2y plus x square y are polynomial functions, therefore they are defined at all points in R3, and these components have continuous first partial derivatives, and curl of f bar is a zero vector, therefore f bar is conservative vector field, and because f bar is conservative vector field, we will have a scalar function phi such that f bar can be written as gradient of that scalar function. So now we try to find out that scalar function. So first we are interested to find a scalar function. We are interested in the scalar function phi, which is a function of three variables, such that f bar, that is given vector field, is equal to gradient of this scalar function phi. Now we try to simplify this quantity f bar equal to gradient of phi. This implies, first we write down vector f bar, which is 2xyz, then first we write x component of f bar plus, I have to write from this x square z plus 2y, jth component is x square z plus 2y times j, and last component is x square y times k. Let me check again, 2xyz x square z plus 2y x square y, 2xyz x square z plus 2y x square y, and by the definition of gradient, this is equal to partial derivative of phi with respect to x times I plus partial derivative of phi with respect to y times j plus partial derivative of phi with respect to z times k. And because we have two equal vectors, their components must be equal, therefore we can write del phi by del x equal to 2xyz, and we give this number 1. Similarly, jth components are equal, del phi by del y will be equal to del phi by del y, jth component is equal to x square z plus 2y, and del phi by del z equal to x square y, del phi by del z equal to x square times y. So we have obtained three first order partial derivatives of required scalar function phi, and we are interested in this value of function phi of x, y, z. So we can start with any of these three equations. If we want to start with equation number 1, we will integrate with respect to x, considering y and z as constant. Similarly, if we want to start with equation 2, we can integrate equation 2 with respect to y, considering x and z as constant. Similarly, we can start with equation 3 also. So that is our choice, but we will use all of these three equations in the process of obtaining the scalar function phi. Suppose we use equation number 1, then here we have partial derivative of phi with respect to x, therefore we will integrate equation 1 with respect to x, integrating 1, and we will integrate partially, that is, while integrating with respect to x, we will consider y and z as constant. Integrating 1 partially with respect to x, we get left hand side is partial derivative of phi with respect to x, and right hand side is 2xyz. So we are integrating 2xyz with respect to x and considering y and z as constants. Therefore, constant of integration must be a function of y and z, because y and z are constants while integrating with respect to x. Therefore, terms containing y and z only, or terms which are independent of x, will be considered as constant of integration. So instead of writing plus c only, we are writing c as a function of y and z. Therefore, now here integral of del phi by del x is function phi. This is equal to, here 2yz is independent of x and integration is with respect to x partially. Therefore, 2yz is constant and integral of x is x square by 2 plus this some arbitrary function of y and z. Therefore, phi of x, y, z, this is equal to, here we can cancel out 2 and we have x square y z plus c of y z. So this is not complete information about the required scalar function phi, because we don't know what is this scalar function or what is this constant function of y and z. So we give this number 4, and now our goal is to decide what is this function of y and z. So for that we can use these two equations which we have not used so far. So if we want to use equation number 3, we will differentiate this partially with respect to z, and if we want to use equation number 2, we will differentiate with respect to y. So suppose we differentiate this equation, differentiate 4 with respect to z, then left hand side is del phi by del z equal to, and we will consider x and y as constants. So here x square y is constant, derivative of z with respect to z is 1, and because this is function of two variables y and z, we will write partial derivative of c with respect to z, and we have value of del phi by del z that we substitute from equation number 3. So del phi by del z by equation number 3 is x square y. So here we put value of del phi by del z, which is x square y, and that we have obtained from equation number 3. So in the bracket we mention that using equation number 3, and you can see this is going to be del c by del z will be equal to x square y minus x square y, that is 0. That means function c is constant with respect to z. So our function depends on y only. So we can write this is equal to, say, h of y, or we can integrate both sides with respect to z, and because we can do in this way also. Suppose we integrate this both sides with respect to z, then integral of 0 with respect to z, and because c is function of two variables y and z, and we are integrating with respect to z partially, therefore constant of integration must be a function of y or only constant. So that is the reason why we are writing this c of yz equal to h of y. I repeat again, here we obtain that partial derivative of c with respect to z is 0. Now we integrate this equation both sides with respect to z partially, and because c is function of y and z and we are integrating with respect to z, we will consider y as constant. Therefore constant of integration can be a function of y also. Therefore we write down h of y here. So now we have obtained c equal to h of y, that we put in equation number 4. So putting this value, of C in 4, we have our scalar function phi becomes now phi of xyz equal to, here we have x square yz plus c, and c is h of y now, x square yz plus h of y, where h of y is an arbitrary function of y or constant. So still we are not having complete information about this required scalar function phi. So what is unknown quantity? Unknown quantity is this one, h of y. So for that we can use this equation number 2, which we have not used so far. So to use this equation, we have to first differentiate this with respect to y. So in the next step, we write down del phi by del y. We differentiate partially with respect to y, considering x and z as constant. So here we have x square z, derivative of y is 1, and because h is function of y only, here we write dh by dy. And now from equation 2, we write down value of del phi by del y. Del phi by del y is x square z plus 2y. So that we substitute here. Del phi by del y is x square z plus 2y, and this is equal to x square z plus derivative of h with respect to y, and here we have used equation 2 to write down value of del phi by del y, and we are interested in dh by dy. So dh by dy will be equal to, this x square z will cancel out and we are left with 2y, and because now h is function of y only, if we integrate both sides with respect to y, we have h of y equal to 2 into integral of y, which is y square by 2, plus some arbitrary constant, say c dash, because now h is function of y only. If you wish, you can understand in this way also. I am integrating both sides with respect to y. So integral of 2y with respect to y plus c dash. This is going to be h of y. 2 is constant. Integral of y is y square by 2 and plus c dash. Therefore, h of y equal to y square plus c dash. So finally we obtain value of h of y that we substitute in equation number 5, and therefore the required scalar function is phi of xyz equal to, let me check what is phi of xyz. It is x square yz plus hy. So first we write x square yz, and hy we have obtained is y square plus c dash, and c dash is arbitrary constant. So this is the required potential function for given vector field f bar, and for different values of c dash we will have different scalar functions phi, such that f bar equal to gradient of phi, and we can check our answer also. If we wish, we can verify our answer. For that we have to find out gradient of phi. So by definition, gradient of phi equal to del phi by del x into I. Del phi by del x will be 2x yz. Yz is constant. Derivative of x square is 2x. This is going to be 0. This is del phi by del x plus del phi by del y. So derivative of y is 1. X square z is constant. Derivative of y square is 2y. This is del phi by del y plus del phi by del z. This is going to be 0. X square y is constant. Derivative of z is 1. So now we can check whether gradient of phi equal to given vector field or not. And given vector field we have to check whether it is 2xyz, x square z plus 2y plus x square y. So now we can check with given vector field. It is 2xyz x square z plus 2y x square y, 2xyz x square z plus 2y and x square into y. So we can see gradient of this function phi is f bar. So this is the correct answer which we have obtained. This is just for your verification. You don't have to write this verification in the examination, but you can confirm that your answer is correct. You have whatever scalar potential you have obtained, that is correct, because its gradient is equal to given vector field. So they generally ask this type of questions for 7 marks in every exam of this type of vector calculus. And this is the third question which I have observed. They have asked to obtain the scalar potential function. First you have to prove that your function is irrotational or conservative, and then you have to find out the corresponding potential function. So first we have obtained call of f bar, which shows that f bar is irrotational, and then using the definition of potential function, which is f bar equal to gradient of phi, first we write down partial derivatives of scalar function phi by comparing these two vectors, and then starting with any of these three equations we obtain value of phi, and we will obtain some arbitrary function of y and z. If we start with x, if we start with y, this c will be a function of x and z, and if we start with integrating with respect to z, c will be a function of y and x. So our role is to find out this function using remaining two equations, and you can see that is very easy. So this is all about this session. I hope you like it. Thanks for watching.